Zeal Education Society, redefining excellence.
Welcome back. In the last lecture, we have seen the cascade realization of pulse transfer function, that is cascade programming. Today we will see the parallel programming for the realization of pulse transfer function, that is parallel realization of pulse transfer function. In this case, the pulse transfer function will be decomposed as addition of n transfer functions or addition of n pulse transfer functions. Let us see how. Let g of z is equal to g1 of z plus g2 of z, so on up to gn of z. And how these are obtained? So by using partial fractions. So what you need to do is decompose the denominator into the pole factors. Now if there is a complex conjugate pole pair, then in that case you have to keep the second order factor. Otherwise all factors will be the first order factors, and then we have to find out their partial fractions and realize them. And then let this be equal to say y of z by u of z, and by this what we get? Y of z will be g1 of z into u of z plus g2 of z into u of z, so on up to gn of z into u of z. And that means for every factor or every pulse transfer, individual pulse transfer function, the input will be u. So the input applied to all blocks will be same, and that is why it is a parallel realization. So here what we do is, say let us consider one case. Let g of z is a upon or a1 upon s plus a1 plus a2 upon s plus a2 plus so on an upon s plus an. So what I have done here, I have decomposed the generalized pulse transfer function into its n poles, and then the partial fractions are obtained, and they are a1, a2 up to an. Now let this be g1, let this be g2, so on up to let this be gn. And then how to realize this? That we have to realize individual pulse transfer function by direct realization. That is not s here, one mistake, big mistake. This shall be z. This will be s in case of continuous time systems. This is a discrete time system, so it will be z. It's z plus a1, z plus a2, z plus a. So now let us represent the first one, that is a1 upon z plus a1. So highest power of z in the denominator is 1, so there will be only one block of z raised to minus 1. This is a1 fed back plus minus, and then here I will get a1. No term of z available here. Z will appear only if it is a complex conjugate pole pair. Otherwise, in case of all real poles, there will be only numbers. Then the next will be z raised to minus 1 block, realization of the second function. Here I will get a2, a1, a2 all, or capital A1, A2 also are the real numbers, any real number. And here I will get this as a2. Then so on. There will be a parallel realization, and finally for this, This will be an plus minus, this is also plus minus, and then here I will have the block of an, and then all will be added together, plus plus and plus. Here I will have y of k, and the input applied to all will be u. This is u of k, and this is nothing but the parallel realization or parallel programming of the given transfer function g of z, which is represented like this. Now what we will do, we will solve the same two examples now by parallel programming, and at the end what you can do, you recollect all the three lectures, that is for direct realization, cascade realization and parallel realization, and solve the examples in combined, that is for a same given impulse transfer function obtain direct as well as cascade as well as parallel realization. Let us consider the example. Obtain parallel realization of pulse transfer function g of z equal to z square plus 9z plus 20 upon z cube plus 6z square plus 11z plus 6. So we have g of z equal to z cube plus 6z square plus 11z plus 6 and z square plus 9z plus 20. No need to factorize the numerator, but you have to factorize the denominator. Now in this case, we get this as equal to z square plus 9z plus 20 divided by z plus 1 into z plus 2 into z plus 3. You can do this on calculator. And the same can be written in the partial fraction form as a1 upon z plus 1 plus a2 upon z plus 2 plus a3 upon z plus 3. And let us find out a1 into a3. So a1 is equal to z square plus 9z plus 20 upon z plus 2 into z plus 3 with z equal to minus 1. So put z equal to minus 1. 1 plus 20 is 21. 21 minus 9 is 12. Divided by, this will be 1, this will be 2. So 2. So this is equal to 6. A1 is 6. Next is A2. A2 will be equal to z square plus 9z plus 20 divided by z plus 1 into z plus 3, keeping z equal to minus 2, and that is equal to, this will be 20 plus 4, 24, 24 minus 18 is 6, divided by, this will be minus 1, this will be plus 1, so this is minus 1, so it's minus 6. And then A3. A3 is equal to z square plus 9z plus 20 divided by z plus 1 into z plus 2 with z equal to minus 3. So this will be 20 plus 9, 29 minus 27 is 2 divided by, this will be minus 2, this will be minus 1, so it's 2, so it's 1. And and that means the transfer function will be 6 upon z plus 1 minus 6 upon z plus 2 plus 1 upon z plus 3. So groundwork has been done. Now we have to realize this. So in the realization, first you have to realize the first one. Z raised to minus 1. This will be 1. And the partial fraction is 6. The next, for the second one, minus 6 upon z plus 2, so there will be only one z raised to minus 1 block. Feedback element will be 2. And this will be minus 6. And then for the third one, it's 1 upon z plus 3. So here I will get the block for the feedback is 3. And this will be 1. Plus minus, plus minus. Don't forget to mention the signs and arrows. And then all will be added together. This will be y of k, and this is u of k, which is applied to all individual subsystems. These are the individual subsystems, this one, and this one. So this is the parallel realization of given pulse transfer function. Let us solve one more example, the same that we have considered in the earlier cases. Example 2. Obtain parallel realization of the pulse transfer function g of z equal to 5 into 1 plus 0.25 z raised to minus 1 upon 1 minus 0.5 z raised to minus 1 into 1 minus 0.1 z raised to minus 1. So let us start solving this one. We have z of z equal to 5 into 1 plus 0.25 z raised to minus 1 upon 1 minus 0.5 z raised to minus 1 into 1 minus 0.1 z raised to minus 1. So what we need to do is, first let us expand this and then convert it into positive powers of z. That is 5 plus 1.25 z raised to minus 1 upon 1 minus 0.6 z raised to minus 1 plus 0.05 z raised to minus 1. And this is equal to multiply numerator and denominator by z square. So this will be 5z square plus 1.25z divided by z square minus 0.6z plus 0.05. And now we have to take partial fractions. But direct partial fractions are not possible because the power of z in the numerator and denominator is equal. So first we have to go for the direct division. 5z square plus 1.25z. Always keep in mind that whenever the power of the z in the numerator and denominator are equal, first you have to do the direct division, and then you take the reduce the power of numerator by 1 and then take partial fractions. Z square minus 0.6z plus 0.05. So I have multiplied by 5. So this will be 5z square minus 0.6 into 5 is 3z plus 0.25. This is subtraction. So here I will get this as, this will be plus, so 4.25z minus 0.25. So this will be minus. And then what I can say, g of z equal to 5 plus 4.25z minus 0.25 divided by, I will take the factors of this as z minus 0.5 into z minus 0.1. So now I have to take partial. Now for this I can take the partial fractions because power of z here in the denominator is 2 and power of z in the numerator is 1. So this is equal to 5 plus a1 upon z minus 0.5 plus a2 upon z minus 0.1, where a1 is equal to 4.25z minus 0.25 divided by z minus 0.1 with z equal to 0.5. And this is equal to, I have to calculate here, so it's 4.25 into 0.5 minus 0.25 divided by 0.4, and it's 4.6875, and let us do it for A2. So A2 is equal to 4.25 z minus 0.25 divided by z minus 0.5 with z equal to 0.1, and that is equal to 4.25 into 0.1 minus 0.25 divided by minus 0.4. So it is equal to minus 0.4375. So I got the partial fractions. And so I can write now g of z equal to 5 plus 4.6875 divided by z minus 0.5, this one, I am putting a1 here, minus 0.4375 divided by z minus 0.1. And then now let us realize this. So we will do realization of this, and 5 directly move from input to output. So it will be for this one, highest power of z is 1, so z raised to minus 1 is minus 0.5 plus minus, then for this factor z raised to minus 1, here I will have minus 0.1 plus minus, the coefficient for this in the numerator is minus 0.4375, and for this one it is 4.6875. 75 and then this 5 is also there. So first let us connect this to u of k, and here I will get y of k plus, and this 5 will come directly from input side to output side, because this 5 does not involve any z. Plus. Just cross verify. Yes, it's okay. So this is the parallel realization of the second example. So in a cluster of 3 lectures, we have seen the realization of pulse transfer function. In the first one, we see the direct realization. We saw a couple of examples. In the second lecture, we have seen the cascade realization. We have obtained the cascade realization of the same pulse transfer functions considered in the lecture number 1, and then we did it for the parallel realization. So this cluster ends. From the next lecture, we will enter in the last section of this course, that is stability analysis of the discrete time control systems. So in about 4 to 5 lectures, we will cover the stability by 2 different approaches or 3 different approaches in particular, and that will end the course. So let us meet again. Thank you.